Hey everyone, thank you for coming to this simulation webinar here talking about the 3D Experience CFD tool known as Fluid Dynamics Engineer. We're going to be going through a basic walkthrough of an early design step, looking at an empty case and just looking at how the air moves through it to identify maybe the best places to put some electronic components. My name is Andrew Smith. I'm a simulation specialist at GoEngineer. Thank you so much for coming out. We're stoked to help you. Please let us know if you have any questions and reach out to your reps if you think this is interesting. Like I said, we're going to be talking about the Fluid Dynamics Engineer role, sometimes called FMK. That's the Dassault Systems Trigram. I may occasionally say FMK when I'm just talking about this tool, but they're the same thing. Moving on, this is the kind of thing we're looking at. I have this simple electronics case. The idea is that air is going to come in the inlet and it's going to go out the outlet, and I just want to see where it's going. So I could probably do pretty easily without using the CFD tool, but it's a good way to show kind of the basics of how to set up a simulation like this. The first step and the flow we see most often is actually people designing their CAD model in SolidWorks and then moving those files to 3DEXPERIENCE to be simulated there and to be managed there. And so I'm going to quickly go through how you can do that. So if you start with on the 3DEXPERIENCE, if you click on the SolidWorks add-in app, that's an app that requires a certain role, but if you have that role, you're able to do this. When you select that, it'll automatically open SolidWorks with the 3DEXPERIENCE add-in open. If you don't do it that way, you can start here by clicking on Tools, then going to Add-ins and selecting Add-ins, which will open up this window, which you can check the 3DEXPERIENCE box to be able to add the add-in. After filling in your credentials, you simply now click on the 3DEXPERIENCE tab in the Task Pane tab. That opens this new window. And if we zoom in, we can see the status. This is the save status. The orange floppy disk shows that the part is not yet saved to the 3DEXPERIENCE. So to do that, I right-click the part name and select Save. When that's done, when that starts, it'll open up the Save dialog window. When it's finished, we'll be able to see that the orange floppy disk has turned into a green check. And we'll also be able to see that the conversion status has turned to an orange clock. This shows us that the file is saved to the 3DEXPERIENCE cloud, but that it's not yet ready to be worked on. After a few minutes, it'll turn from an orange clock to a green check, showing that it's ready to be worked on. Now, in order for us to work on that, we got to select the item. So we simply click on it, left click. It'll highlight it in blue, and then we can click on the compass and select the Fluid Scenario Creation app, which I have in one of my favorites here. It's important that you make sure that that part is highlighted in blue before you select the Fluid Scenario Creation app. Otherwise, it'll open the Fluid Scenario Creation app without the part in it. But if it's highlighted in blue, it'll open it up with the part in it like this. So here I have this simulation is ready to go. First thing, I'm going to rename it to Webinar Elec Enclosure, all without box, and hit OK. So once that's done, it takes us into this sort of user interface, and I'll walk you through that really quickly. We have here on the right side what's called the Learning Assistant panel. The Learning Assistant panel there on the right. The Learning Assistant panel gives us a nice, clean, step-by-step way to go through the CFD process on 3DEXPERIENCE. We have up here the steps. For example, model is an important step, and then the commands that are used to complete that step. These commands are here for convenience, but they're all also located down here in what's called the action bar. The action bar has two components. It has the command right here on the bottom, and it has the section tabs above that. So to navigate, I can switch apps here with these commands. So I can switch to scenario. Once I'm in the scenario app, I can choose a section tab and then define section tabs. But for our purposes, we will be staying, we'll just be using the assistant. That's going to, again, it's nice, it's clean, and it's a straightforward way to set this up. The last part of the user interface I want to talk about is just the tree. Tree is here, and it shows you where, basically, once you've completed a command, it'll fill in the tree until we have the all the parts filled in. All right, so let's get down to it. I'm going to start with model, and I'm going to do model setup. Model setup, the model setup command actually contains several of these other commands. So we'll start with that. It's nice and easy. Before we get too far, I just want to mention, we're not going to be getting into the deep details of a lot of this tool. There are probably thousands of options that we can tweak and change, and we don't have time to go over that. And really, this is supposed to be a high-level introduction to the tool. So I'm not doing heat flow, I'm not doing external flow, we're just doing internal flow on air, and so that's probably the last time I'll say that, or say something about that. But to define the fluid material first, we select this magnifying glass, and it opens up the material palette window. To find what we're looking for, we can just search in the filter bar and then navigate through the library. You can see here I have air. Once I select it, I hit OK. And that's done defining the fluid material. The next part is defining the fluid domain, or the fluid domain bounding parts. This is really simple with a single part. I just leave it as is. If I had a complex assembly and wanted to ignore some of the components or change what was going to be bounding my flow, I would select what parts I want ignored. But again, we're doing a really simple case with just one part, so I'm going to leave that as is. The next part is identifying the regions. Now, we're required to have fluid regions here in the CFD tool. And so I'm going to name this the inner region. There's only one, but like I said, it's, I think, worth renaming everything. And then I just choose a wall, a surface that's touching the fluid, or that will be touching the fluid. When I do that, you see that this blue cube appears. This is what the SO systems calls a glyph. These glyphs are used to represent abstractions. So this one is going to represent the abstraction of the fluid region. And that's all I need to do for that. I can erase that here and flip which direction it goes on to here. I'll leave that as is for now. I can also define openings. Now, I don't have to define openings. For example, if I have a circulating flow, I can leave it as just a closed container. But I do have openings. I have two. I have an outlet here that you can see as a square, and an inlet here you see as a circle. To create those, I click on the blue plus twice. Again, I'm going to rename these. Makes my life a lot easier when I know what things are. Then I'm going to identify the support. For this inlet, I'm going to choose the edge propagation tool. You can see this selection toolbar shows up. I'm going to choose edge propagation and choose just one of the edges on the inlet face, right there. Now you see another window pops up saying I can propagate this edge, and I have different ways to propagate, and then I can choose, other parameters. But this will work for me to be able to select all both of these edges, and then you'll see this new glyph. Again, this glyph appears, which represents the inlet opening. And that'll be useful later. Then I'm going to go to the second opening, call it outlet, click on the no selection spot in the support window, and I could try this again, but I should have known that's not going to work because I'm selecting a face that has angles that are, not going to work. That was my fault. I should have paid attention. But you'll notice that a glyph still shows up, representing that opening. And this obviously isn't what I want. And this is a nice physical or a visual way to verify that the inlets or outlets are where you want them to be. So clearly this isn't. So I'm going to remove that there, and I'm going to just choose the edge selection tool and select the individual edges. And now you can see my glyph is right in the middle, right where I expect it to be, about the right size. And so now I'm done with openings. You'll notice this mesh pull-down menu as well. I don't need this right now, and I prefer being able to choose my meshes later on as I get there, but I can kind of mess with it here. But for now, we'll just leave it as is, and we'll figure out the mesh later. So now we can see, oh, hey, my model step has a nice green check next to it. That means I'm done with that step. It doesn't mean that I'm necessarily done with all of it. It means that the simulation can now run as far as that step's concerned. If I had other stuff I want to do, I still can. I can add porous sections. If I wanted to add that, I can add additional materials or potentially additional fluid regions. I'm not going to do any of that, so this is, in actuality, all I need from this step. So let's move on to the next one. Now you'll notice this one has a nice red circle around it. This means that I can start on this step, but that nothing's been started on it yet. So I click on the step, and it opens up these new commands. Physics behavior. This is just defining my physics, or excuse me, my fluid and solid physics here. So I'm going to leave that as is. The state's fluid. I want it to be in the turbulent regime, but I can choose other regimes such as laminar or inviscid. And I also have the option when my turbulent viscous regime is selected to select other turbulence models such as the shear stress transport K omega model, the Spallard-Almaris model, or the realizable K epsilon model, which is the one I'm going to go with. Each of these has pros and cons, and that is a conversation probably for another time. To really dig into where they vary and how they could potentially benefit your design using a different turbulence model. I have these other effects down here. Again, we're going for real simplicity here, so I'm not going to worry about any of these. And that's all we need to identify and define the fluid physics. Once that's done, you'll notice I still have my red circle. That means I'm not finished setting this up. The next step here is defining the solver setup. So we have two options here. We have a steady state step and a transient step. They're called steps because they can be added together. So I can use both a steady state, I can use a steady state step first and follow that by a transient step. So you can have sort of like, these are the initial flow conditions. And then at some point I have something that changes and it's going to vary with time. I'm going to start using a transient step. So you have these options. We're only going to be using a steady state step for this simulation, and it's going to be real simple. I'm not going to talk too much about any of this, but these are like where you can get into lots of fine control over your simulation behavior and your solver behavior. The only thing I want to talk about here is the difference between error thresholds and residual thresholds. Now, I'll talk about this a little bit more later, but residuals are the common way of deciding whether or not a CFD tool is converged or not, the solver is converged or not. But Dassault Systems has introduced this error parameter as well. And like I said, I'll talk a little bit about that while we're going through the solver, but I just want to point out here, this is where you define it. And you can choose to only look at residuals or only look at error or some of each if you want. So these are nice to use like that. But yeah, more on that later. So now I've finished my model, I've finished my physics, and again, I could add another transient step here if I wanted. I don't want to, but that, even though that's green check, I can still add more. Now, initial conditions, I don't want to add any, but I could, if I was looking at heat transfer, define the temperature of the solids and the fluids here. If I was looking at mixtures, I could define mass fractions. But I do want to add some boundary conditions. If I solve this now, which technically the solver will attempt to solve this, it'll solve it'll solve a box of unmoving air. I don't want to do that, so what I'm going to do is I'm going to set up some boundary conditions here. The first one I'm going to do is a velocity inlet. I do that again. I'm in the boundary step. I select velocity inlet command. And now it's asking for a support. That's real easy. I have a glyph here, if you remember me talking about that earlier. And that's easy. I select that, and I'm ready to go. I can choose a different velocity if I want to. I'm going to leave it at 1 meter per second, just for easiness sake, and I'm good to go. Now I need to define the last one. Obviously, if I have air flowing in, I need to have air flowing out. So I'm going to choose a pressure outlet and define this outlet glyph. So you see, it's nice that I renamed these glyphs because now it tells me, yeah, that's what I want. And I'm going to have a gauge pressure of 0, so that's about right too. Now I've defined my boundaries. I have sufficient boundaries to work. I could add more if I wanted to. Any solid surface will default to a wall, so that's nice. Moving down, I get zones and loads, so I can apply these porous zones and volumetric heat sources, rotating regions, stuff like that. Contacts is similar. I can identify and define fluid interfaces, stuff like that, solid interfaces. And then output requests. I got about a couple more things I want to do before we run the actual simulation. The first one is to talk about output requests. So I can define a new one here, but before I do that, I want to show them over here in the scenario tree, flow analysis case tree. I have my outputs. I'm going to expand my output requests. There's 3 of them. And I double click, and that pulls up the window to edit. First thing I'm going to do is rename this as whole. It's called whole flow. So this is taking into consideration the whole model. And it shows me the things that are going to be output and the rate at which they're going to be output. So this will save one frame every, looks like 1 million frames, 100,000 frames. I actually want probably 1 every 5. The smaller this n is, the more time it takes to run the simulation because it has to save all the data every. So if I only want to look at it at the end, I put in 1 million and it'll only give me the results at the last step. But if I want to look at the details, I want to be able to make videos. I can choose this number, make it smaller, but it will take longer to save the files every step. And then I can choose what things are being saved. So, for example, I don't care about any of the electromagnetic stuff, so I can take that out. Everything's single phase, so I can also take out my multi-phase thing if I wanted to. I can also apply pre-selected defaults, and it'll reset that to what it initially was. I'm going to leave that like that and hit OK. So now that's redefined that output to whole flow. And then I'm going to change these ones too. These are nice to be able to just get some data from the inlets and outlets. But like I said, I like to make sure that they're changed to be appropriate and that they're easy to read, so I like to rename them. Now I'm going to make one more output request. This one I'm going to call Y plus. So Y plus is a parameter that, let me pull that up real quick. Y plus is a non-dimensional length, and not to get into the weeds too much, in terms of usage, we want to keep our Y plus value between 30 and 100 or less than 5. What happens at 30 to 100, actually anything over 30 is going to create a wall function. Anything under 30 is going to resolve the flow. So the wall function is going to approximate what that flow would look like, where a resolved flow is going to solve the Navier-Stokes equation to get the boundary layer shape and behavior that way. It's recommended that we have a value either of between 30 and 100 or less than 5. If it's less than 5, then we have a good resolved boundary layer. If it's between 5 and 30, we'll still resolve the boundary layer, but it won't be sufficiently resolved, so we'll have error that'll come in. If it's over 100, there's a good chance that we're going to be missing out some serious stuff, and we're going to be missing out boundary layer details that we need. I've shown the equation here if you're interested. This is something that's a little more advanced CFD, but long story short is your Y plus value is going to tell you how, if your mesh is sufficiently refined to capture the boundary layer or to approximate the boundary layer. And if we find results that are too high or in between 5 and 30, then we may need to remesh those locations. So I'm going to define a new output of y plus. I'm going to select this selection tool here, face propagation. I'm going to select a face, and you'll see that it gives me the option to propagate by angle again, and that works for me. I'm just going to look around real quick to make sure that these other faces are blue as well, to show me that they're in fact selected, and then I'm going to select these ones too. And then, oops, the inlet faces as well. So now I've selected all the interior faces. And like I said before, Y plus has to do with the mesh size, so it's going to look at the mesh closest to the wall, and I want to be able to capture that in all these places. It's technically a turbulence variable, so I'm just going to do that, and we'll leave it like that. So now Y plus is defined on all the faces. Now the last step before we can run the simulation is to mesh the model. So if I'm continuing in the same process I've been doing, I click mesh in the steps. Now, for some reason, it has a check mark by it, which is weird because I haven't meshed yet. And then I can click on this hex dominant mesh. Point out real quick that I already have a hex mesh here. And when I click on this, I create a second hex mesh. You don't want to have two hex meshes. It'll cause error, and the solver won't solve. So instead of doing it like that, I'm actually just going to double click hex mesh over here in the tree and just edit it this way. So I'm going to leave everything as I can. Initialize from support is a button that just basically looks at the characteristic length, area, and volume of this model and uses an algorithm to define the max min sizes of the mesh. This is a good place to start. I have run this study already a couple times, and I will put in something that I've already run that works pretty good. You'll notice I have added boundary layers. It tends to converge a little bit better if I have a decent boundary layer here. And I've chosen the first layer thickness. This is the thickness of those prismatic cells that are right against the wall. The first one's going to be 0.05 millimeters, and then the number of layers. I can choose to, I can work with these options to do some different meshing, but I also have local meshing that I can do. So I can either choose to enhance and refine the mesh on certain faces or features, or I can make a Cartesian box that has mesh refinement in it. I don't need to do any of that now, and I can hit OK, and that'll close this window, and it'll save those settings so that when I go to simulate, it'll make the mesh. But I want to double check and make sure that visually this sort of looks like what I expect it to look like. So I'm going to hit mesh, and that'll start the mesh generation process. Which takes just a minute. Okay, now we can see, I can see some mesh. That's really nice. I'm going to hit OK. But I can't really see the details here. That's a little annoying. So fortunately, there's this thing called the Visibility Manager. You can access this by right-clicking in the blank space and selecting Visibility Manager. This will pull up, and I can dock it up here with my assistant. In the Learning Assistant panel, now I have this docked here. I can actually make it so that I don't see the mesh, and I cannot see the body, and I cannot see those, and I can make these things all visible again as well. What I really want to see, though, is the mesh here. So I'm going to get rid of the shape and zoom in a little bit. Okay, that looks about what I thought it would look like, but I want to know what it looks like on the inside. I will again right-click in the empty space here, sectioning. This will cut it in half, but I want to be able to see those meshes. So I'm going to unclick that so that it doesn't cut through everything, and that I can see the mesh as it is. That looks good. That works for me. Close. Now I think we're ready to run the simulation. So I will click on Simulate. When I click on Simulate, I get these three commands: model and scenario check, simulate, and simulation status. When I click Simulate, it will automatically run the model and scenario checks beforehand, and then it will automatically show the simulation status. If you've closed the simulation status, you can click this button to pull that back up. I'm going to go ahead and click Simulate. If I had a really long study that I wasn't planning on running right now, but maybe want to make sure I could run it when I'm getting ready to head out and want to leave it running on my computer, I'd probably run these model and scenario checks first, and then later, before I run, I'd hit the Simulate button. I don't want to be solving those problems right before I'm letting my computer run overnight. So I'm just going to click simulate because this is a pretty quick solution. And it'll take just a minute for that to pop up. And now I have another window with some solver options here. I can choose a location. Locations are basically local or on the cloud. If I choose on the cloud, I can choose from among 4 configurations. I can solve for free 16 cores, even using cloud computing. Additional cores cost additional credits, and you can buy credits from Dassault to be able to have access to this larger solving power. And up to 16 is free for both local and on cloud, but using above that requires additional computing power. And so I'm going to use 16, I'm going to use local, and hit OK, and it starts. It takes just a minute here for this to get up and running, and then we can talk about some of the features we'll see in the simulation status window. Now that the Windows simulation status window is up, I'm going to just talk about these. There's 5 tabs here, and we can talk about these as we go through it. But the first one shows messages. These are going to be things, obviously, like errors, warnings, and information. To start out, we don't want errors. Errors usually mean that the simulation is not going to work properly. A lot of times we'll have errors that say, for example, you have 2 meshes. Can't solve. Another one is, or warnings are going to be stuff like this. Variable heat flow was not found. I have no heat transfer here, so there's no heat flowing. So this variable is not available, and this is letting me know. And same with bad cell. Bad cell would be identifying my mesh, how it was not refined enough in some spots, or if I have a high aspect ratio of some of my elements. This will let me know about that too. Licensing messages usually only show up when there's a problem. If you lose internet connection, you'll have a licensing message saying that we can't connect to your license, or if you need to sign in to 3DEXPERIENCE again. I'll talk more about plots in a moment. Iterations gives us details about each increment, each iteration, and the error and residuals of those. So you can look at those details. And then diagnostic files has some really interesting information, but it basically has everything that we've put in and everything we could have put in is available in this window. So I can see how many elements I have here. I can see how many of those are hexahedral elements, how many of them are octahedral wedge elements, and so on and so forth, tetrahedrals, everything. And so that can be interesting to help me troubleshoot a little bit. I can look at my material models. So I'm using air, it gives me its conductivity, density, specific heat, and viscosity. No load curves. So I'm not going to go through all these because there's millions of them, probably thousands. But just like, I'm going to use the implicit run-get-cutted Gauss time integration. I'm doing a steady state, so that's going to be 0. But anyway, so you can look at every equation and all the coefficients that are associated with them. Here's my K epsilon realizable turbulence model and the coefficients and constants associated with it, and so on and so forth. I'll skip down a little bit to the bottom here, and it's going to show me increments, time, and then those same residuals and errors, as well as my min and max velocities in the X, Y, and Z direction. Now you'll notice in the Diagnostic Files tab, I actually have 3 sub-tabs. The status, which again is probably a more detailed version of some of this other stuff we've looked at. And a log, which is going to basically tell us the start and the stop behavior. So you can see these warnings again. Before we get too much further, I want to talk about these plots. So I talked a little bit about error and residuals. And the long story short is that residuals are sort of the industry standard for deciding whether or not a solver has converged, meaning that the error is small enough to consider the results sufficient. We typically require in industry residuals that have dropped 4 orders of magnitude, so going from 1 to 0.0001. I think there's one more 0.0001. Oh yeah, that's right. So part of the problem can be that if we have a initial condition that, say, has flow going the wrong direction, so I have just a simple pipe flow, and I'm going to say, initially the flow is going to be flowing backwards. And then I start running my solver. My solver is going to start with that error that comes out of that, which is going to be really high. And then as the flow starts to turn around, that error is going to drop really fast. And so I will achieve quote-unquote convergence from a residual perspective really quickly. Another possible scenario is where I have I input the flow down the pipe perfectly, so that or really close, so that when the solver starts solving, it starts with a really low actual error. So when it tries to reduce those residuals, it can't. So you have sort of a stubborn solve. The error allows us to basically say, look at the trajectory of the residuals and, without getting into the real technical details, basically say, oh, this is even though it says it's resolved, or the residuals say it's converged, we still need to work on this more because the initial guess was bad. Or, hey, even though we can't get residuals to go 4 orders of magnitude smaller, we actually are getting, it's sufficient, the error's not changing. We're getting where we should be. So it can be a little bit more conservative and reliable way of ensuring that you have convergence. And there'll be more on that later as well. For now, I'm going to let this run, and we'll pick that up once it's finished. Okay, now that my solver's almost done solving, you can see I've gotten my results down from quite high in my error to 0.01, which is 1% here, which is what I wanted. And you can see it's extracting results now. I'll get a nice little green check up here when this is done, and my close will go from grayed out to available to be clicked on. And I will also get, there's my green check, there's my close. I will also get my diagnostic file. So what I get in the diagnostic file now is in the data, if I scroll to the very bottom, I now get peak memory usage, statistics, time statistics, which can be really nice, and like total memory usage. So some nice stuff there. In the status, at the very bottom, I think that just says the analysis has completed successfully. And then in the log, I get another just batch of data here that just basically tells me the time it finished, is what I really care about. So I have start time and end time here if I want, as well as that time data in the data step data tab. Now that I'm done, I can just hit close, and boom, there's my there's some pressure. There's a pressure result. This is the default. This is nice. This is going to be from my whole flow output request. And I can look at all my results here. So I have, for example, pressure. If I select velocity, right click, and then hit activate, deactivate plot. So I activate that one. Now this is obviously pretty boring because we have the no slip surface condition. If I want to look at the details, I go down here to display in the section tabs, plot sectioning, and I can choose the axis I want to cut normal to, and get some results. There's more details here we could talk about another time, but for now we'll leave that as is. You get the nice little plot here. I can also look at velocity vector plots. And I can also animate these plots. Now, if you remember, I chose to simulate this every 5 increments. So you can see it's running through them, then every 5 I get an image. So this isn't working because I need to actually say, I want to do it every 5 frames. Then I can also save that video if I wanted here. Now we'll try that. There we go. Watch that again when it gets done solving that or saving those videos. So anyways, you can see the nice little animation pop up. It's nice looking. I can also choose to look at different things. Now, if you remember, I talked about Y plus earlier. Y plus is something that's basically a surface phenomenon because we're only looking at those values on the surface. We're looking at the distance of the first cell from the wall and using that as the length to use in our non-dimensional length scale. So to do that, I need to first create a new display group. I do that by clicking on the Display section tab, and then under the Display Group action, it pulls up this window. This is showing me what the display group 1 actually is. I'm going to create a new display group, and I'm going to call it Inner Wall. I will use the initial state of display group 1. That just means that it's going to basically be a copy at first of display group 1. What I can do now is actually select different items to be the thing that are displayed on. So for example, I only want to display the values of Y plus on the wall, on the inner wall. So what I'm going to do is I'm going to choose Entity, Surfaces, and I'm going to choose Surface Probe 24. I'm going to replace the current selection, which is the whole model. Now this takes a little bit of work to get this to go through, but yeah, that's something that's going to be talked about in another content piece to work out how to create display groups and what they are used for and how it all works. For now, I got my surface probe on my inner surfaces of the inner walls, so that's what I want. But what I want to see, if you remember, is the Y plus value. So what I go to now is Plot, Contour Plot. I select the variable I want, which is Y plus, and hit Apply. Now I had to move which frame I was looking at. I was just looking at the initial frame, which has no data in it. And I go to the last frame, which is my resolved, fully converged flow situation. And now you can see I got results. Now remember I said that the Y plus value needed to be between 30 and 100 to be able to use the wall function, or under 5. Now you can see I got values from pretty small, 0.0016, up to about 3. So those are good. Those, as far as I'm concerned, they're sufficiently refined. In fact, they might be too refined. And I want to know where they're too refined. And I can kind of like poke around and try to find it. But it's hard because this all is the same color blue, except for right here where you can see these big ones. So what I'm going to do is I'm going to alter my legend. I can do that by double-clicking on the legend itself, and then I can edit these values here. I'm going to make that a half and close, and that's that. And here we have the Y plus values spread out here. I can see, okay, yeah, these are good, these are big. And really what I'm looking for is the biggest possible cells relative to the flow characteristics there that won't cause problems with the meshing. So I have big ones here, those are fine. But what I want to find out is where are the ones that are too small. So I can see here, oh, this is dark here. This is dark blue here. This may be still not quite as excuse me. It's probably not quite as refined as I want. So I'm going to change this again to, let's say, 0.2. Set up. Oh, there we go. Now I can see a little bit better. Yeah, I got some really small values in these corners, and these probably ought to be, well, I could make these a little less refined if I wanted to. Even here at 0.1. So I could probably make the mesh on the inside of the whole container quite a bit larger while refining in just these local locations, refining the mesh to make it a little bit more acceptable. There's also the option I can create, for example, let me pull this up in Plots, Streamlines. Okay. And once these are done, it's going to automatically switch me out of that into another one. So what I want to look at actually is the velocity on the Streamlines. And so now I can have, oops, turn this around. I have the high-speed flow. You can see it gets some swirls happening. And so, like I said before, if we were looking to put electronics in here, I kind of have a good idea. We probably would have had anyways, but I can see, okay, right here, I want to put my heatsink right where the flow is fastest. Right here would be a bad place to put anything that's going to be producing heat. And that's, you know, nice. It was obvious, but these are kind of the tools that we could use to get to that point where we could see that better. In later content pieces, when we have additional heat transfer happening here, we could, we'll get into that more. Thank you so much for watching. Please contact your rep if you have any further questions about the capabilities of the fluid dynamics engineer role. He can connect you to any of the simulation specialists here at GoEngineer that can help you answer any questions you have, or if you want to request a demo or have, like I said, any technical questions, please reach out. Thank you so much, and we will talk to you again soon. Thank you.